Hello folks and welcome to Lesson 1.2, Transformations of Linear and Absolute Value Functions. So we're going to be looking at some of the transformations that we had talked about in the last section, specifically in how they relate to linear and absolute value equations. So we're going to look at a horizontal and vertical shift and the reflection over a line in this particular section. We're going to save stretching and shrinking for another day. So let's take a look first at a horizontal transformation. So what a horizontal transformation is going to do is it's going to take this equation or any graph and it's going to shift it to the right or to the left. So we can move it to the right and we can come up with the exact same graph but going to the right. What that does is that actually takes each one of these individual values and it moves it to the right h units, whatever h units are. And or we can actually move it to the left. So again, we can take any one of those points and move it to the left horizontally. And what that does is that gives us the same y value, but a different x value when we move the graph. So you'll see the format of what that may look like up here in the box. The graph of y equals, we read that as f of x minus h, is a horizontal translation of the graph of y equals f of x, where h cannot equal 0. We'll get to what all that means here shortly. So what we're going to do is we're going to subtract h from the input values before we evaluate the function. And when we do that, the graph will move left when h is less than 1 and right when h is greater than 1. I'll show you what that means here shortly. We can do the same thing with an absolute value graph. It works exactly the same way. So each one of these values, let's pick some points. So like this point right here, and we got a couple different points on the actual curve. What's going to happen is when h is positive, I'm going to move it to the right. That means I move each one of these points to the right, however many units. And I can also move these points to the right, however many units. What that would give me is that would give me a different line. Or I could move them to the left. So I can move, again, each one of these individual points to the left. Okay, and what would that give me? That would give me, again, an entirely different curve. But it will look exactly the same as the original curve, just shifted to the right or to the left. We can also move the curve vertically, up and down. So again, same idea. We have these different points on the line, and when k is positive, we will move these points up, k units. And what does that give me? That gives me, again, this same shape of a graph, just shifted up. Or, if k is negative, we'll move them down. And again, we'll get the same shape of the graph, just shifted down k units. Same happens when we're looking at absolute value graphs. Again, these points will move up when k is positive, or down when k is negative. Okay, let's take a look at an example problem. Let f of x equal 2x plus 1. Write a function g whose graph is a translation 3 units down of the graph of f. And then part B, write a function h whose graph is a translation 2 units to the left of the graph of f. Okay, let's take a look at just part A to begin with. So g of x, we know, is a function where we've taken the function f and we moved it down 3 units. So what does that mean? That means we've taken f of x and we've moved it down 3 units. So f of x plus k, this is a k movement because it's vertical, right? Up and down is vertical movement. So we know it's f of x plus k. And since we're moving down, we know in this particular problem that k has to equal -3. So what I'm going to do is I'm going to rewrite my equation and know that g of x is equal to f of x plus -3. Now, we would never write it that way. We'd write it as f of x minus 3. We'd write it that way. Now, okay, so now here's the thing. You have to remember this is function notation, right? This is function notation. So what I'm going to do is I'm going to replace f of x with what f of x is equal to. And that's this equation up here, 2x plus 1. So g of x equals 2x plus 1 minus 3. And now I just combine my like terms and rewrite this as 2x, let's see here, plus 1 minus 3 is minus 2. And this is my new function, g of x. So let's take a look at the graph, right? So the graph's over here on this side, and if you look right here, this red line is the equation we started with. That is 2x plus 1. And if you take any one of these points, you will notice that I have moved them down 3 units. Pick any point you want at all, and we've moved it down 3 units. And we've come up with a new graph. And that new graph, if you remember from Algebra 1, has a slope of 2 and a y-intercept of negative 2. So this equation right here is y equals 2x minus 2. Let's take a look at the second part of this particular problem. Okay, so part B, h of x. h of x is the graph of a translation 2 units to the left of the graph of f. Okay, so this means that h of x, well, if I think about what the function notation, this is left 2 units. So if I think about what that was in the general form, I'm looking at f of x minus h. Okay, and since I'm moving to the left 2 units, I know that h is equal to negative 2. Okay, so what's that mean? That means that my function h of x is going to equal f of x minus my h value, which is negative 2. Okay? Now, again, we wouldn't write this minus a negative. That's not the way we write it. We would write it as f of x plus 2. That's the way we would write it. All right, so now I have to look at function notation. And I know h of x is equal to f of x plus 2. Now, if you remember, with function notation, this means that you're supposed to replace the x in equation f with x plus 2. So that means if we go up here to this top equation, this x isn't here anymore. Instead, it's replaced with x plus 2. So let's see here. What would we have? We'd have 2 times x, but it's not x anymore. It's x plus 2 plus 1. And now we just have to simplify and do our math. So let's see here, distribute. So I get 2x plus 4 plus 1. And let's see here, that would give me 2x plus 5 as my equation. So now if we look at the graph and we pick again any point we want, let's look at this one, maybe this one down here. And if you look, when I move to the left 2 units, I end up with my new equation. So the red line again is y equals 2x plus 1, the one we started with. When I move to the left, I end up with my other equation, which again, if you remember from Algebra 1, has a y-intercept of 2 and a slope of, a y-intercept of 5 and a slope of 2. We get the equation 2x plus 5. All right. So right now I want you to pause the video. This can be a little tricky, so I want you to pause the video right now, and I want you to give this problem a try. So let f of x equal 4x minus 9, and I'd like you to write a function g, that is the translation 5 units up, and the function h, who's 1 unit to the right. Okay, try it out. Go ahead and pause the video here. I'm going to give you the answers momentarily. All right, let's take a look at example A. Okay, for A, we know that g of x is equal to, let's see here. Well, we're doing something to the graph of f, it says so. So f of x, and I'm moving up 5 units. So that means I'm looking at k. So f of x plus k. So what is k? Since I'm moving up, k is equal to positive 5. All right, so we'll rewrite our function. G of x is equal to f of x plus k plus 5. All right, so g of x is equal to, what's f of x? F of x is the function 4x minus 9. I get that up here, okay, plus 5. And then I'll combine my like terms. And I'll end up with 4x minus 9 plus 5 will give me minus 4. Let's take a look at B. B, we're looking for the function h of x. And h of x is equal to, well, let's see here. We're moving it right 1 unit. So right 1 unit, that is a horizontal shift. So that means I'm looking at f of x minus h. And in this particular problem, since I'm moving it to the right, I know h is positive, and it's equal to positive 1. So I'll substitute that back in. H of x is equal to f of x minus 1. All right, so now what do I do? Now I'm going to take this, x minus 1, and I'm going to plug it into function f. Function f's up there at the top. So let's see here. H of x is equal to 4. It's not x anymore. It's now x minus 1 minus 9. I'll go ahead and simplify this by distributing. So 4x minus 4 minus 9. I'll combine my like terms, and I'll get 4x minus 13 as my final answer. All right, our second transformation is a reflection. And there's two different ways that we can reflect things. So here's the first. This is a reflection about the x-axis. And when we reflect across the x-axis, what we're doing is we're viewing here this x-axis, the horizontal axis, like it's a mirror. And what that means is when there's a point above the x-axis, it gets reflected over the axis and goes the same distance from the x-axis on the other side, like a mirror. And we can do that with any point. So again, this point would reflect over the x-axis and end up down here. Now this point is directly on the x-axis, so it's not going anywhere. And this point right here is below the x-axis, so it will be reflected above the x-axis. And what I end up with is I end up with the same shape, but a reflected version of that shape that goes over the x-axis in the other way. So how do you do that mathematically? Mathematically, what we're doing is we're multiplying all the outputs by -1. And it essentially changes all their signs. One of the really cool things to notice is that the x-intercept, this point right here, doesn't change at all. We can also reflect across the y-axis. So again, the same idea, except that this time, the y-axis, the vertical axis, ends up being our mirror. So we have a point that is on the right side of the y-axis and is reflected over, and turns out that it's on now the left side. If it's on the axis, it of course doesn't move, but we can pick any point. We can pick this point right down here that's on the left of the the y-axis, and it gets reflected over to the other side, the same distance away. And what we end up with, again, is the same shape, but it is reflected over the y-axis. Mathematically, what we're going to do is we're going to put the negative sign inside the parentheses of the function that we're looking at. And we're multiplying the inputs by -1, or changing all of their signs before we do any further math. The other thing I want you to notice, just like in the reflection over the x-axis, where the x-intercept didn't change, when you reflect over the y-axis, the y-intercept stays the same. With the absolute value graph, if we're going to reflect things across the x-axis, right, what does that mean? That basically just makes the u point downward. It's pretty easy to see with an absolute value graph. But what if we reflect an absolute value graph over the y-axis? What happens? Well, this point, which is here, would be reflected over and go here. This point that's to the left of the axis would be reflected over and go here. And we end up with the exact same graph again. So reflecting an absolute value equation over the y-axis doesn't change the graph. At least if that's the only transformation you're doing. Let's take a look at two example problems. So, example 2, let f of x equal the absolute value of x plus 3 plus 1. Write a function g whose graph is a reflection about the x-axis of the graph of f. And then part B, write a function h who's a reflection about the y-axis of the graph. Okay, part A. According to the rule, when I'm writing g of x, what does that mean for me to do? When I'm reflecting across the x-axis, according to the rule, it means I should take the opposite of f of x. Okay, so what that really means, and a way that might be easier to write it, is if we change this negative sign to -1. and then we can say times f of x. That might be a little bit easier to see. So what I'll do is I'll take g of x, and I'll say that that's equal to negative 1 times whatever f of x is equal to. Well, what is f of x equal to? That's the absolute value of x plus 3 plus 1. Okay, the important thing to remember is that I have got to distribute this negative sign to both things. Okay, absolute values don't go inside, negative signs don't go inside absolute value bars, so be very careful of that. When I simplify this and distribute, I'll get negative the absolute value of x plus 3, and that plus 1 would change into a minus 1. So here's a graph of what we have looking at here. So the red line is the function f of x, which is the absolute value of x plus 3. And if we look, the function below here, this blue line, is the reflection over the x-axis. So here, if we again view that x-axis as a mirror, we see that this point, which is 1 unit above, becomes 1 unit below. This point, which is 4 units above the x-axis, turns into 4 units below the x-axis. This point that's over here, that's 3 points above the x-axis, turns out to be 3 points below the x-axis, and we have our new graph. Let's do part B. So for part B, we were looking for a function who was a reflection about the y-axis. Okay, so let's write out what that looks like. So h of x will equal, well, if I think about what that reflection about the y-axis looks like, and I think of that rule, it was f of negative x. So what that means is I take function f, and every time I see an x, I replace it with negative x. Okay, so h of x equals, and if I look up at my function, that's the absolute value of, okay, it's not x anymore, it's negative x, plus 3, plus 1. All right, so h of x, if I simplify that out, I get the absolute value of negative x plus 3 plus 1. That'll actually work. That'll actually be an okay answer. But we're going to look at some things and compare this to a graph. And if you look at the actual graph of that, the red equation here is my original graph. That's the absolute value of x plus 3 plus 1. And if we compare the points, you'll see that this point is 3 units to the left, but now it was reflected, and now it's 3 units to the right. This point right here, which is 1 unit to the left, is now 1 unit to the right. This point that's up here, which is the 6 units, is now 6 units on the other side. And we end up with our equation there. Now, this is a little different. Let me clear this all off of here. Let me just erase everything. Because what we'll find is it also kind of looks like my graph was moved this direction 6 units, which means it could in fact be a different equation as well. And we're going to talk more about that, but let me show you some of the math that you could do. You could, in this equation, h of x equals the absolute value. What you could actually do is you could factor out a negative 1. And when you factor out that negative 1, you get x minus 3 on the inside of those parentheses. And then what you can do is you can actually split up your absolute value bars. So you could write h of x equals, and you can split this up to be the absolute value of negative 1 times the absolute value of x minus 3 plus 1. And we know the absolute value of negative 1 equals 1. So our final answer could also be the absolute value of x minus 3 plus 1. It's a matter of which form you see. So this answer will work or this answer will work. They're both technically correct. Now, the one that's down here at the bottom is the better answer because it's simplified down more. But we'll worry more about that later. So at this point, folks, I'd like you to pause the video. I'd like you to try these two problems out, given this f of x is equal to the absolute value of x minus 5, minus 4. And again, I'd like you to pause the video. I'd like you to try these two problems out, and then I'm going to give you the answers. Go ahead, pause the video. Okay, so for part A, we're looking for that reflection about the x-axis. So I know that g of x is equal to the opposite of f of x, negative f of x, based upon the rule that I know, that reflection about the x-axis. Okay, so when I rewrite this, g of x is equal to negative, and I replace that with the absolute value of x minus 5 minus 4, and it's that whole quantity, and I need to remember that. That's very important. The next thing I'll do is I'll take and I'll distribute through my negative sign, so I end up with negative the absolute value of x minus 5 plus 4 to remember to distribute the negative. And again, if it's helpful, you can write that as negative 1 times the absolute value of x minus 5 minus 4. It might be helpful to think of it that way, and then distributing the negative doesn't seem so weird. All right, let's look at B. For part B, we were supposed to write h of x, and h of x is a reflection about the y-axis, and again, that rule would be f of negative x. So again, what we're going to do in the original equation, we're going to replace the x with a negative x in the function f. So let's see here, h of x is equal to the absolute value, it's not x anymore, it's negative x, minus 5 minus 4. And again, if I just drop those parentheses, I end up with the absolute value of negative x minus 5 minus 4. And again, that answer would be acceptable, but if you wanted to practice the algebra and keep going, what you could do is inside your absolute value signs, you could factor out that negative 1. And once you factor out that negative 1, let me go up here. Once you factor out that negative 1, you can split up your absolute value to be the absolute value of negative 1 times the absolute value of x plus 5 minus 4. And when I simplify that down, I'll end up with h of x being equal to the absolute value of x plus 5 minus 4. All right, guys, I hope this was helpful. Please make sure you fill out that reflection form that is posted below, and I'll see you in class.